Thank you for the introduction, Reza. So I'm going to talk a little bit about programming the 2.0 stack. And some of you who have read my blog post on Software 2.0 might know what this might refer to, and some of you who haven't might not, but it will become clear very, very soon. So I actually want to start by telling a story. The story starts 1 million years ago. And this is us 1 million years ago, and we're kind of mostly preoccupied with gathering, hunting, and smashing rocks, and making sounds at each other, and things like that. That's what your daily life is about. And then a bit later, we kind of like developed fire, and I promise this will make sense, by the way, in just a bit. So we developed the fire, and then we developed agriculture, and then we started building pretty amazing mechanical machines. So here's a mechanical machine. This is an early steam engine. And then we started to miniaturize things. So we started to actually develop computers, first mechanical, and these are mechanical computers, and then electrical. And so things are going along quite nicely. And here we are about 50,000 generations later, and we're actually writing code and doing pretty amazing things. So we're kind of on a roll here. But under the hood, it's actually like kind of a similar, still kind of like a monkey brain from 1 million years ago, only 50,000 generations. So it's kind of incredible how far we've come. Like, we've actually built some pretty amazing things. So really good job, everyone. So we're just ingenious, right? We've broken down all the problems, we've figured them out, we've engineered the heck out of them, and things are actually working really well. And so we were really on a roll until we met our match. At one point, humanity has decided that it's useful to try to recognize things inside images, and for example, like detecting cats. And the tried and true approach of designing and engineering and breaking down problems and kind of taking this giant array of pixels and figuring out what's in it has become kind of intractable. So people have tried in the early days and tried to engineer our way around it. This is a lot of like Lisp schemas. This is taken from Shrewdloo, which is, by the way, an amazing project from the 1980s. Then we try to we're going to break down the problem. We're going to figure out, first we have to detect these small pieces. Then we have to write code for detecting maybe small ear pieces or eye pieces. Then we're going to stitch them together. We're going to come up with all kinds of elaborate schemes for how we're going to decompose the problem of visual recognition. And we're going to write kind of code for every one of those pieces independently. And then we're going to plug them together. And we're going to recognize everything in the world and just fully invert graphics and things like that. And this kind of like didn't work very well for a while. And it was really difficult to get this to work on just arbitrary images. So then a bit later, we started to realize that if you just put a tiny bit of machine learning, instead of kind of like writing all these programs from scratch, something that worked for us in the past, instead we're going to write all these feature extractors, and we're going to develop them. And then we're going to have just a tiny bit of machine learning on the top there. So we're going to have a small linear classifier. And that started to work a little bit better. And so we designed some of those features, and then we handed off a little bit of that to the optimization. And so then we went kind of wild trying to design all kinds of features. So this is from a paper in 2011, computer vision paper, kind of describing a number of features that you would extract from an image. So things like hogs, and I don't know actually half of these now. But basically, there are 3 pages in the paper just devoted to the feature design. And that worked OK for a while. And then we figured out that actually, if you take humans and human design and human ingenuity out of the system, and you just do more computation, and you hand off more to the optimization, things almost always work a bit better. So let's forget about all that stuff that humans have designed with all their ingenuity, and let's try to just have a single kind of blob of compute, like a ComNet architecture, and let's try to hand off more of the design to the optimization. So the optimization finds the feature extractors, not just the final layer on the top, but actually all the feature extractors in between. And this trend has not stopped, right? So when you look at some of the most recent architectures and some of the things that are working best now on image recognition, we haven't stopped at, we've been hand coding architectures because we're trying to be clever. Again, there's this, and actually if you step away again, things can work better. So now we're actually thinking about, this architecture should not be designed by humans. We're not very good at designing things. Let's kind of step back again, and we have bigger computers, bigger data sets, and let's hand off even more to the optimization. So now we're also optimizing over the architectures. And so really the trend has been, it's kind of like, I would say that image recognition and more generally any kind of problem that is complex kind of pattern recognition, we tried to design our way into it. And what we're finding is that with more compute and with more data, the trend is towards less designing and more computing. So in the beginning, We can afford to hard-code images, hard-code some solutions for small problems, but that's not going to get you to Google, Facebook, Tesla scale. And then we're actually untying the optimization, giving more into the optimization, and things are working a bit better. So as part of this trend, this is what I kind of described the software 1.0 versus software 2.0. Software 1.0 is things like C++. A domain expert sits down and writes down the algorithm for, say, recognizing cats or something like that. You decompose the problem, design algorithms one by one. You compose them into a system, and you measure the performance, and you do your best trying to engineer the system. And software 2.0 is kind of this, it's basically neural networks. You're not writing code in C++. The code is now written in the weights of a neural network, but we're not writing that code. The optimization is writing the code. We are massaging the data sets for the most part and coming up with the infrastructure for optimization. But for the most part, we can measure some objective, like classification error, and then we're paying a large price in compute to try to find programs, really, that are doing a very good job according to the performance metric. So this is not only working very well in image recognition, it's also working well across many other disciplines. One of my favorites, of course, is AlphaZero or AlphaGo. Again, say we're playing chess. Again, human ingenuity, we always have this urge to try to design a solution. And Stockfish, for example, is a pretty amazing program for basically, it's an AI for chess that's been written over time, and it's a giant code base, and it incorporates a huge amount of heuristics from domain experts in chess. And then, as we've seen, if you just put a giant convolutional neural network on it and run it for a very, very long time, because you have an objective that you can measure, you can just pay in compute to search the program space for solutions that actually play chess extremely well. And so it's actually kind of humbling to look at some of these results from AlphaZero. It's just, you're looking at the performance of this neural network, this COMNet, over time. And we've been playing this game for thousands of years. I'm not sure exactly how long, in case of Go, for a pretty long time. And we've been writing these algorithms for years. And then, AlphaZero, basically, you have to write the infrastructure for maybe a year or 2 or 3, and a number of people have to work at that. But once you're at that spot, you can actually learn to play chess in just a matter of days on these computers. And these computers are not only getting faster. So we see this not just in chess, but we're also seeing it across many other kind of disciplines. When you look at state-of-the-art results in many kind of disciplines that look like pattern recognition, you'll see that most of the state-of-the-art papers is just COMNet and recurrent neural net architectures all over the place. So it's really taken over this transition from 1.0 to 2.0. I have to add an asterisk to this, by the way. The asterisk is that one of the most impressive robots, which I think is probably Boston Dynamics right now, they have super amazing robots, and they recently came to give a talk at NIPS. And the person from Boston Dynamics was making fun of all the machine learning people because they're like, this is all fully software 1.0 code. There's no, forget deep learning, there's no machine learning in the system. So this is really it's pretty amazing that this works. It's actually almost like an asterisk to my thesis here when I'm trying to get a point across here. So I would, of course, try to argue that this is amazing, but it will top out, and that when we put the infrastructure in place to actually learn all of this, I think it's going to be overcome. There's a few benefits to Software 2.0 stack I wanted to point out briefly, just that this transition actually has a lot of fruit. So first of all of these neural network architectures that we're building out are extremely computationally homogeneous. So this is not a sprawling C++ code base. This is just a lots of conv and relu stacked up at inference time, which is pretty amazing. Because these are so computationally homogeneous, they're very easy to bake into silicon, and we're seeing some of the first ASICs coming out recently that really take advantage of this property because it's not too difficult to actually put this on hardware. Then these stacks, this code, has beautiful properties that it has a constant running time and constant memory use. So think about your C++ code base. You could run into infinite loops, and things take more or less time at different points in time, depending on the inputs. This thing always runs the same amount of time and uses the same amount of resources, and it's completely kind of deterministic. So that's a really nice property to have. For example, in systems like, for example, the autopilot, where we actually want to make guarantees about the system performance in various ways. And another kind of nice property of the system is that it's extremely agile. So if I come to you and I say, I'd like the exact same functionality, but you have to run at exactly half the time because I have some kind of a resource constraint. So I want exactly half a running time. In case of C++ code base, if the autopilot, say, is written in C++, this would be an extremely difficult effort. You have to bring up your profiler, and you try to like shave off pieces of code until you're at half a time, if the whole thing is a giant COMNet, then I'm going to remove half of my channels, or I'm going to take out some layers, and I have something that works a bit worse, but runs at exactly half the time faster. So that's kind of amazing that we can just do this. We can just retrain for arbitrary demands from the system. And finally, of course, it works really well. So that's an easy one. I'm not going to go into details here. So I wanted to talk a little bit about this transition going on from 1.0 to 2.0 that is happening at Tesla as well since I joined. So Tesla is kind of a robotics company to some extent when it comes to autopilot. I mean, the car itself is basically a robot. It receives inputs, and it has to act in the world and act intelligently. In this case, we have two actuators. We have the steering and the acceleration, but a lot of things kind of stream into the stack. And at Tesla, we actually have the largest deployment of robots in the world. We have about 250,000 robots out there in the world, which is kind of cool. And our task is to make them autonomous. Now, when I kind of joined, of course, the stack, as I mentioned, takes in a number of inputs, but only two scalars come out, steering and acceleration. And when I kind of joined, it was, of course, there was some kind of a convolutional neural network doing a lot of the base visual recognition. But there was a lot of pre-processing, a lot of roboticsy code, a lot of post-processing. So kind of a meld of 2.0 and 1.0 stack in the system. And kind of, this has kind of been happening over time. And so the 2.0 stack has been kind of growing. I'm going to give some examples in a bit. And of course, it's so tempting for a deep learning person to come into this kind of a problem, just look at this and be like, oh man, two numbers are coming out. Things are coming in. Oh man, this is like expanding. It's just like so tempting to just color the whole thing green. And you have infinite data because people are driving and they're showing you what the outputs should be in any case. It's just so tempting, right? But for now, we're taking a kind of a measured approach. Just to give you a sense of an example of this expansion and what that looks like to make this slightly more concrete. Suppose you wanted to recognize parked cars, which we actually want to do quite often. With a 1.0 approach, again, human ingenuity approach, you would try to, for example, design a parked car detector. So of course, we have a detector for cars. And suppose we have these detections, and we know that they're cars. COMNet gives this to us. And then we say, OK, well, a car is parked if, suppose we track it for a while. And a parked car will probably not move for a while because it's parked. So a car is parked if we're tracking it and it doesn't seem to move. And maybe there's some kind of a particular pattern of arrangement of cars. And maybe it's on the side of a lane in like something like that. So we can try to write some post-processing code to actually detect this. Or you can be like, this is all kind of not right. And car is parked if a COMNet says so, and just based on a lot of data. So humans can annotate a lot of this data quite easily. And then we can actually just fold this into the COMNet. And that's an example of taking 1.0 code, putting it into 2.0 code. And of course, it's probably not too hard to believe that this would work better because the COMNet has so much more context than what we're seeing in this reduced representation. Because the COMNet has all the raw pixels, and it sees all of the context of all the lane line markings, and it sees that they're lined up here. It looks like a parking lot. I mean, there's so much more context in the pixels than any of this high-level representation. So this transition has really borne some fruit, and it's going along quite nicely. We actually shipped a product. We shipped an update to the autopilot just recently, as a week or two ago, and it's going really nicely. And people kind of love the update because it drives much better. And there's a lot of people who posted a lot of YouTube videos, and it's very rewarding to kind of see a lot of the feedback because people kind of love the update. So you can also try to look it up a bit later. Now, I wanted to talk a little bit about programming the 2.0 stack and really being efficient at it. So in practice, when you want to get this stuff to work, I had to kind of like learn a lot of things on spot because I'm coming from a PhD background. So what I'm kind of used to is, you're given ImageNet data set, and you have to design a model and an algorithm. And so you spend a lot of time kind of thinking about what's a better model, what's a better algorithm, what's a better training regime, et cetera. If you're actually trying to get this to work in practice, it looks very different. So here's my PhD. Data set is given to me. Usually it's ImageNet or something like that. And I'm mostly worrying about the models. And when I came to Tesla, I mean, we still worry about the models. But oh, man, it's just like the things I lose sleep over is just like significantly more the data set. Accumulating it, massaging it, cleaning it, sourcing it is just a complete disaster. Not even just massaging this data set and getting a good set of it, but even, OK, so some lessons to dive into this a little bit. First of all, as I find out the hard way, even the data labeling itself is like super non-trivial. So coming up with what you should be labeling in images. So for example, of course, we have a self-driving car. we, of course, want to stay inside lane lines. So, well, OK, so it makes sense to actually recognize the lane line markings in the image, right? So how hard could that be? Let's just label, OK, there's a lane line. There's a lane line. OK, that's great. And then you try to launch this, and you try to annotate lane lines. And all these kind of edge cases kind of start streaming in, and it just makes your head hurt. So for example, what do you do in cases like that? This is somewhere in Europe. It's actually pretty common. We see this quite often because Autopilot is a global product. Do you follow the lane line markings, or do you just like interpolate? I don't know. I don't know. It's like I'm not sure what to do there. What the hell is that? It's like, I don't know. What the hell is that? So of course, like, do you annotate with it or through it, or I don't know? Just imagine these kinds of philosophical conundrums for like hundreds of cases for every single thing you want to annotate. It just makes my head hurt. Because of course, like, I'm not sure if should the control stack after us take care of this, or should the vision stack take over it and just say, OK, well, this is like you should just go through. Not obvious, right? Suppose you want to detect objects. So we put bounding boxes around objects. How hard could this be? Like, we want to put bounding boxes around these vehicles right there. Well, it can be very hard. So I don't know. You come across stuff like this. And now it's not obvious. So is this 4 objects? Is this like 2 objects? Is this 1 object? And now you have to be consistent, and now you have to put this into your labeling documentation, and now the labeling documentation is 100 pages, and now people annotate it incorrectly because it's so messed up and confusing. You want to try to annotate traffic lights. How hard could that be? It's like, red, green, orange, I don't know, put bounding boxes around traffic lights or something like that. It can be really, really hard. So, like, what the, I don't know what that is. I don't know what that is. There's a blue traffic light. I didn't even know this. So our labeling documentation for a while didn't even have like blue as an option. So people came across this, and they're like, I don't know what to do. And I'm like, me neither. I guess we have to add the blue color. I'm not sure. You want to do speed limits. How hard could that be? It's just a number. You should move at that speed. It can actually be like very, very difficult. So this just becomes AI complete very, very fast, because speed limit is like 25, after 6 p.m., if you're a truck, during the full moon, like, I don't know. This one I hope is a joke, but I wouldn't even be surprised if it wasn't. I'm not 100% sure. Lots of problems, like, for example, somewhere in Europe, we saw this traffic light which said, like, 60 ends here. So basically, you have a default speed limit, I think, of I don't know what, and then they're letting you know that the zone of exception, 60, like, ends there. So from now on, you revert back to the default speed. And of course, if our car was driving by and recognizes 60, it's just going to exactly do the wrong thing. So anyway, so that's OK. So that's what I lose sleep over. That's one thing. Lessons learned the hard way, number 2. In a lot of these cases, these labeled data imbalances can be huge, and they actually matter. And if you're going to put software 2.0 stack on top of them, you have to really worry about it. So for example, in our data set, if you look at the bounding boxes and their classes, you'll notice that 90% of all objects, moving objects, are cars. There's a huge amount of cars. And for example, there's not too many trolleys or streetcars. So the ComNet is not very good at recognizing those because it has like 1,000 examples, and we have like a zillion examples of that. So now you have to really worry about that class imbalance. Speed limits are similar. 45 is the most common speed limit, as it turns out. About 10% of all of our signs are 45. And then you have many other that are significantly more rare. Where this gets actually interesting is, suppose I want to annotate, say, we're interested in detecting cut-ins, right? Because we need to control to that. So of course, you want to potentially detect that the red blinker might be on. But the problem is that most of the data, of course, people do not have the blinker on. It's such a rare event. So now I need a huge data set of that. And it just happens once every, like, now and then, pretty rarely. I'm going to end up with 100 examples of it, and now I'm in trouble. The same problem we have with orange traffic lights. Orange traffic lights are pretty rare. They just kind of appear for like 1 second. And so we have a zillion of red and zillion of green, but we have very, very little of orange. And then the network just like gives up. Doesn't really like to predict orange traffic light because it never occurs in the training data. So that makes a lot of sense. So now you have to worry about that. It's not just the class distribution, but also the data distribution. If you just sample uniformly at random from the fleet, you will notice that most of it looks like this. It's a straight highway. This is where most people drive. That's just what you're going to get. And then when you try to train on top of this data, and then you try to use the autopilot in some pretty rare situation, then of course that's not going to work very well. We don't have too many snowy scenes with not very good lane line markings and so on. And we don't have very many scenes where the kind of slope is like extreme, and of course ComNet will not like it. So now you need to massage that data distribution to get this to work well. And what's even harder is that in these self-driving cases, it is precisely these rare examples that are so critical to get right. Like you can't just have a rare example in your test set and just get a zero accuracy on it, because some of these could actually be like critical, right? So here's an example. So we're driving down the highway, and there's this thing that extends into our lane. I don't actually know what this is. It's just we grabbed this from an intervention clip. I don't know what this is, but now you have to kind of like worry about, okay, how do I annotate this? How do I label it? How do I avoid it? How do I get 10,000 examples of it at the very least, or 100,000, and make sure that we train on it and make sure we recognize it and deal with it appropriately? I saw this bird attack the camera, just swoops in from the sky, attacks the camera. That's a lot of fun. How do you make sure the ComNet doesn't kind of like freak out or something like that? Make sure it's robust to it. This car over there dropped a ladder. And of course, you're driving here, and suddenly there's a ladder in your way, so the person just like takes over and does this pretty unsafe maneuver, right, to actually avoid the ladder, which is completely necessary in this case. So now if you're driving in autopilot, and of course we can potentially recognize that there's something in the way, but if it's a ladder, then of course you want to try to do this maneuver to evade it. But if it's a plastic bag, then maybe you recognize that that's actually something you could drive through, and suddenly you don't want to actually risk this like pretty risky swerving maneuver to put other people in danger. So suddenly you have to actually recognize, okay, is this something I can drive through or not? And now how are you going to get like a data set of a million things where there are things in your way, and some of them are safe or not safe, or how do you deal with this, right? And these are such rare cases. So this happens maybe once, every, in a blue moon. Luckily at Tesla, we have, as I mentioned, 250,000 cars on the road, so we actually get stuff like this pretty frequently, much more frequently than probably the other players. And so we can actually have some hope of addressing some of these questions, as long as we're careful and as long as we write the stack around making sure we catch all those things and that they end up in the training data set. And the last thing I kind of wanted to briefly talk about is that the toolchain, basically, as I mentioned, a huge amount of fight is not just over the modeling and the algorithms. It's about creating a robust training set, sourcing all the hard examples, massaging the data set, cleaning it, maintaining it, et cetera. And this is what you do when you try to get Software 2.0 stack to work in practice. And it seems to me that we've developed pretty elaborate tools to help us in the Software 1.0 setting. We have, for example, IDEs that are pretty complex. You have a debugger, a profiler, syntax highlighting, go-to definition. Lots of things help you write the Software 1.0 code. But there's really nothing that helps you write the 2.0 code. Or rather, we don't write the code, but the code is implied by the data set. And we have no tools to help us build and massage these training sets. So what does a IDE for Software 2.0 stack look like? It probably helps you with a lot of the tasks that I see on a daily basis that really I lose sleep over in terms of massaging this training set and getting that to work. So we have our own guests, and we're designing our own thing. And I'm kind of hesitant to go into too many details at this point. But we just are building a lot of back-end infrastructure for creating these data sets and making sure that in any case that is pretty rare, how do we find it? How do we source it from the fleet automatically? How do we annotate it? How do we make sure it's all clean? How do we have a uniform distribution over all the cases that we're worried about? And just putting all of this in place is a pretty elaborate effort. So that's extremely important. And I don't think that people are kind of, as I mentioned briefly here, it's kind of not in the spotlight. Because what's in the spotlight is how do I train giant like NASnet at scale, and that's important. And we do a lot of that too at Tesla. So we have computing clusters, and we worry a lot about training these networks, iterating on the architectures and getting them to work really well. But really, a lot of it is worrying about the data set. But if we do our job well, then we're going to make these beautiful cars and all of its friends drive really well. And if that works really well, people will want to buy the autopilot, and people will want to buy the Tesla cars. And then we might have a beautiful future. This beautiful future is electric, it's sustainable, it's autonomous, it's sexy, and it's just exciting. This is the future that we want to be part of. And really, the sky's the limit if we get this to work. So if some of these problems excite you, and if you want to help us out and build the Software 2.0 stack for these extremely important problems in the world, then I encourage you to get in touch with us. One of the ways is to email vision@tesla.com. That kind of hits my team. And yeah, that's it. Thank you. can take some questions.
Yeah, so we have some time for questions. Please come up to the mic.
Hi, Andrej. Thank you very much for the presentation. Two things I don't know if you can answer, but even before anything related to adversarial examples in the physical world, even just the example with the ladder, let's say it was just a truck with the signs, right, that does road repairs, and the stop signs fails. And the camera recognizes the detector, it's a real stop sign, no adversarial, how do you deal with it, for instance, and also with everything related to things like, the basic catastrophic forgetting, right, you keep learning and etc.
Sorry, so your first question was about adversarial examples? Or,
No, I said even before adversarial examples,
okay.
You have a truck that does road repair, has signs, stop sign fails.
Yes.
It's a real sign, no adversarial. How can you deal with such real-world example?
Absolutely.
And second, same thing in the same sense, because obviously you're describing a very huge to-the-moon effort of annotation and etc. But for instance, even problems, as you said, the basics of data, it's not really basic, even catastrophic forgetting, right? Things that you already learned, but now things change over time.
Yeah. So I guess for the first question, one of the things that we take a lot of advantage of is the shadow mode. And this is really helpful because we recognize all of these stop signs, and then part of the control stack recommends that we should start stopping right now. And then we can see what humans do. And some of the humans might just disagree with that assessment. And whenever they do, that's a really good trigger. And make sure we capture it, make sure it streams in, and make sure, again, that we have this really elaborate backend that allows us to analyze these issues and make sure that they end up in the training data. And then you have a slightly less chance of screwing up in that particular case in the future. Turning that crank over and over. And I like your question with respect to even before you get to adversarial examples, because that's a good framing, because a lot of people ask me about adversarial examples, and it's like, I'm mostly trying to stay in the lane, mostly trying to not, so it's like we haven't even gotten there, I think. But yeah, at some point this will become really, really interesting to think about.
I guess there's a slight overlap with this question, but you're young enough to remember that you went to statistics class. They told you that the training set has to absolutely represent the exact same distribution as the test set. So when the system is deployed, if there is a statistical shift, you're in trouble. And then that was the statistics professor with the long beard, and then there's a machine learning professor say, you have to find all the right examples. You have to enrich for the tragic cases. Do you think that one day machine learners and statisticians will sit around the table and decide if it's still true that you need, what distribution do you need?
Yeah, so the problem is we don't want to work in the average case. We want to work in the worst case, right? And that's kind of where this discrepancy comes in, is that if 90% of my driving is on the highway going straight, I'm probably at some point going to, at some point the comp that gets it, and it's really not helpful to get a zillion examples of it. So that's why we kind of have to oversample in these rare situations that, as I mentioned, are performance critical. So if you're chasing the average performance, then it probably makes sense to actually have your training data set be exactly what you see at test time. But what we care about is making sure that we work really well in all the rare cases as well. And that's, I think, where some of the discrepancy comes in.
So going back to your early slide where you showed the evolution of computer vision, you have this sort of code gen portion and sort of the upward projection. How do we know learning the weights is something that we can scale, even if we have enough data? Is there any early evidence of that, or?
How do we know that? Sorry, can you rephrase, I guess?
So the code gen part, you basically, develop a system that can learn the weights. Is that something because the projection goes straight up, standard hockey stick? Do you think is it something that we know will scale even if there's enough data? Is there some maybe threshold, some complexity that could prevent it?
Yeah, I'm pretty optimistic about the wide trend. It just seems like with a small amount of compute, you can't afford to search a very large program space. So in the beginning, we just searched the space of linear classifiers on top of features. And now I have more compute, so I can extend the search space, and I can still find a good solution. Those are ComNets. And then now that I have even larger computers, I can actually expand that search space again and still hope to actually, for this to work, I can find good solutions. So it's just a trend I'm seeing kind of evolve. I guess we haven't seen it break. I'm not sure if, this will certainly work. We still hardcode a lot of things. We still hardcode that gradient is the credit assignment mechanism, backpropagation and so on. and we still hard code the fact that we're using stochastic gradient descent. But really, at some point, you have a training set, then you do some compute, and then you're supposed to work well. And some compute right now has a pretty specific structure of like, okay, I take batches, I do forward, backward, I do update, and this thing you can unroll and you can just see as a single TensorFlow computational graph on top of your training data set. So at some point, we might potentially just get rid of even that structure. Okay. And that's probably what's going to happen.
Okay, sure, thanks.
Hi, on the topic of massaging your data and picking the right data sets, how do you deal with bias in the case that the right action isn't clearly defined? For example, I have the choice of hitting either 2 children or 3 adults, or like 2 black people, 2 white people. How do you deal with bias in that kind of a situation?
Yeah, it's kind of like a trolley problem restatement, or yeah. Yeah, for a lot of this, so we don't currently deal with it, I guess, explicitly, because we're not even at a point where we can actually like detect, say, like some of these things. I anticipate that probably what will end up happening is we're going to adopt, because these will be machine learning systems that will inherit human driver behavior. So we'll probably end up inheriting some kind of distribution of how humans behave in these cases, and hope to start off from that and try to make it, of course, better. But you end up probably with behavior that is kind of like the average human, or of those humans how they would behave in those kinds of scenarios, hopefully some of the better humans. There are ways of imposing basically these reward functions. You don't just have to take these demonstrations and learn on all of them, but you can prefer some demonstrations over others. So like, for example, the acceleration should not be too high, and of course, you should not be hitting things. So you can prefer some human rollouts from others. So you can hope to basically, at best, imitate some of the best human drivers. And I think that's kind of how it's going to turn out. Yeah.
Would it take into account anything about like how many passengers the driver has inside of the car? For example, figuring out what would be the best case if I have 4 people in the car versus hitting 1 person?
Yeah. So currently, we can't even like detect that, I guess.
Okay.
So we haven't like really written these kinds of super explicit rules. This is absent from the stack. We're kind of we're driving forward and trying not to hit things. So.
Yeah. Just hitting things is inevitable, kind of like Uber this past week.
Yeah. Sorry.
So
Great, thank you.
Thank you. Thanks. Let's thank Andrej one more time.